So what I'd like to do is introduce the equations of motion and expose you to additional steps in integration and how we can evaluate things with limits. There is a more in-depth derivation of these that I posted online done by a gentleman called Dr. Schuster. He does a fantastic job. It's a great visualization. This one I'm just going to kind of focus on some of the mechanics and how you can see how we can describe motion. Oops, let me do a shape. So I'm going to start with a graph. There we go. And with my graph, let's do velocity. Velocity in meters per second and time in seconds. And for this one, I'm going to have some fun, and we're not going to start at the origin. I'm going to be like, here we go. So that tells me that I have some V initial. And my question for this one to start off with is going to say, well, what do I do if I want to find what my velocity is at like this time? A little line down here. So this would be like T final, whatever we want to call it. So I wanted to know what that velocity is, and so how do we figure that out? So let's see. What do I know? I know that I have a line, and I know that I have an intercept. And before you might be saying, well, Linda, you did graphs and you showed us how to do integrals and derivatives, and now how the heck do I do that? This is a line. This is something that you have seen over and over again. We're just now actually going to use it. And this, hopefully, looks familiar. The equation of a line. So what do we have? We say that this y here tells us where on the y-axis we are, given some slope and some x component for this line. And then this is this portion here, I'm doing a different color, that would be our intercept. So let's see. Let's write those pieces in. So this is my intercept, my initial velocity. This is going to be my final velocity. This is the slope of the line. And if you recall from the last video, we did the slope of the line for this. Let's see, that's rise over run. So rise is this guy. So V final minus V initial divided by T. And then you look at me and you say, but we have, oh, that's V final. Sorry about that. We have all of those things here. But let's also remind ourselves what this is. That thing there, that's just acceleration. So this m here is actually our acceleration. And this x, that's our time. So now I can write that in one pretty equation. And I get that V final equals acceleration times time plus V initial. So let's see if that makes sense. That says if I start off with some initial velocity and I'm accelerating, then my final velocity is going to be this added piece of speeding up time, or speeding up plus the initial. I'm going to be going faster when all is said and done, unless my acceleration is in the opposite direction of the velocity, in which case I'd be slowing down. So there we have it. Oh, that looks just like this. I can rearrange this. I can go V final minus V initial. Let's see, now I'm going to do it in steps. V final minus V initial, just moving the V initial over to this side, equals AT. No problem. If I want to say, I don't know, let's move time over, and I'll get V final minus V initial divided by time equals acceleration. Well, I feel like that's what we just did over here. So we used the information from the line to derive an equation, and come to find out that equation is just using the definition of what acceleration is. Nice. So our fundamental pieces are change in velocity over time, defining how much we're accelerating, or our change in position over time, defining our velocity, is very helpful, very fundamental, and very helpful information to work with. So now let's say I want to do my displacement. So let's see, we've defined that one. if I want to do my displacement, I can look at this. I can say, okay, so I can do that graphically as well. I can find the height and do the area of the triangle and then the area of the square if I'd like. Or I can do a little trick here. I can look up at my two definitions that I have here, and I can rewrite those. I'm going to move the dt's to the other side. I can say that dt equals my change in velocity, the dv, divided by a. And then move the dt here and the a down below. I get dt equals dx over v. Now, as in with any math, if two things equal each other, then we can set them equal to each other. So that's what I'm going to do. I have dv over a equals dx over v. Beautiful. Now, if I want to do anything with this, I can notice I have a dv and a v. So I'm going to move the v up here, and just for fun, move the a over here. It doesn't matter. I'm going to explain that in a second. You can leave it wherever you want. If you're like, why would I move that? You can leave it alone. That's okay. You just need to remember that it's going to apply to everything on the opposite side of the equation if you're going to move it around after. All right, but I do need to move this one because I have a dv and I have a velocity. So that can't stay on its side. It needs to go with its d component. So I have, whoops, not a. So I'll have v dv equals a dx. Now what I want to do is integrate. So whenever I have these differentials, these d's, if I want to make them go away, I integrate to make them go away. So I can integrate. And remember, the whole thing we're trying to get to is how to define this area. So I'm going to integrate that. So let's talk this through. What am I going to integrate from? So this would be some sort of v initial. Because remember, I put my line up top. It doesn't have to be 0. Because some v final. And this isn't a dt. This is a dx. So this is going to have some initial position and some final position. Very well could be 0. If we move our axes, it can be any number of things, but we're just going to do it in general terms for now. So how do I do this? Before I've shown you how to take integrals, but I haven't done it with any limits. We haven't applied anything to it. So what we do is we write out, I'll start with the velocity term. I have velocity. I'm going to do my integration. Well, it's v raised to the 1. I add 1 to it. So that gives me my v squared. And remember, if I take the derivative of this, I better get that thing back. So I'm going to divide by 2. And now we're going to take care of these limits of integration that we have. And we do that by denoting it with this line. So v naught to v final. Now what the rules are here is that I'm going to evaluate this variable at that position, time, velocity, whatever it is. And then I'm going to subtract the thing on the bottom. So you can think of it as I'm writing it like a subtraction. This minus this. So let's erase that though. So this is going to go to then, this goes into that v that's squared. So it's going to become v final squared. Let's not forget our 1/2. Our v final squared. Then minus, I put this into this variable. Minus my v initial squared. There we go. So I've done this side. Now let's do that side. So that's going to equal, let's see, a doesn't have an x component in it, right? We've defined it up here, so we're not going to do any fun math tricks with it to change it into anything. So this is just a constant. My acceleration isn't changing. That means it's a constant. So the other way I can write this, I can say, so that equals, I can pull any constant outside of my integral. X naught to x final dx. And this is fun. So I'm just integrating 1. Well, so it's, or you can think of it as I'm integrating x to the 0, right? Because anything exponentiated to the 0 power just equals 1. So I'm adding 1 to that. So I'll have a So that's just going to become x, and I'm evaluating that from x initial to x final. So the way to write that then is a times, now remember I'm going to put this variable here into whatever it was I integrated. So I'll end up with x final minus x initial. So let's pull that all together. I end up with then this 1/2 times v final squared minus v initial squared is going to equal this piece. So equals a. One of the ways that we can write this is with that delta, because that just means a change in. So that delta sign says just the change in the amount that we've used, right? So I can write that as a delta x. And then I can say, well, if I want to solve for, I don't know, if I wanted to solve for position, I can, let's see, move, I can go 1/2 v final squared minus 1/2 v initial squared. Oh, and then all of that divided by a. Ooh, that's getting ugly. So I have 1/2a times v final squared minus v initial squared equals delta x. But the more common way that you see it is just moving the 2 over to the other side, and generally we'll use this expression if we want to go like v final squared, if we want to solve for it, v naught squared plus 2a delta x. Oops, delta. I'll leave the delta in there. And that's it. So what I highly suggest that you do is repeat this process without looking at it. So watch it and then kind of talk your way through it if you haven't done the calculus before, just to get comfortable with how to do these things and how to treat the integrals. But more importantly, when we look at it graphically, I want you to know that we can pull all of that information out from a graph, that the tools that you've used before, they still apply. We can still use them. And now our next step is going to be actually applying things to that and seeing what happens when we throw things, drop things, cars take off, cars slam on the brakes, all sorts of fun things.